everybody to our seminar. It's my pleasure to introduce the speaker of today, Professor Karin Baur from University of Leeds, and she will speak about Frieze patterns and cluster theory. Please.
Yeah, thanks, and thank you very much for the invitation. So I want to talk about Frieze patterns today and cluster theory, but eventually it's going to be about representations for some algebras. So let me first recall what a Frieze pattern is. In combinatorics or mathematics, this is a pattern of integers or elements of a integral domain, where we start with a row of zeros, and then we have a row of ones, and then we want, whenever we have a little diamond like this, A, B, C, D, that AD minus BC equals to 1. So it's like if you turn it around slightly, you have an SL2 determinant rule. Okay, well now I cannot really write. So the order of this Frieze pattern is the number, and then you have positive integers. And eventually you see there were ones again and zeros. So in between the zeros and ones, there are some more interesting rows, and the number of those is called the order. So here we have order 4. And Hochstetter has introduced this notion. Yes.
On your right-hand side, there are some tools that you can write some arrows or some lines or something.
Yeah.
Maybe it is helpful if you can see on your right-hand side. Yes, the first one, you can choose the pen, you can choose the color, and
cool.
then you can write down with your actually mouse. It's not very convenient, but sometimes it's helpful. Yes. But now you shared the screen, I think.
Sorry?
I think, what did you do? It's okay. You first should choose your pen first, and then the color.
Yeah, I did that. I wrote M.
Okay.
Can you see that?
No.
Oh.
Did you draw something? No, I can't.
Yeah, I wrote where you see order.
Yes, we can see.
I wrote a large M, or
yes.
like a small M.
Yes, we can see it.
That's what I did.
Yes.
That's all.
Okay, thank you.
Okay, and for here it is equal to 4. Yeah.
Yes, I can see, yes.
Okay, good. Oh, thanks. Yeah, so the entries in between the zeros are positive integers here. You can do that more generally. You can just take elements in an integral domain. And we always want the diamond rule. And yeah, so Hochstetter and Conway studied those in 1973 in 2 articles, which gave a lot of properties. So under these conditions, you can show that this is periodic. You have a glide, a translational symmetry. So if you go far enough to the right, it will repeat. Here we have the number 1. That's, well, not obvious, but it's the repetition of that 1. So here we have 7 steps, and then everything repeats. And the period is a divisor of m plus 3. So here m was 4, so the period could be 7. It has to be 7 here. There's no non-trivial divisor. Also, there is a glide symmetry, which I will show in the next page. These Frieze patterns have been studied a lot in the recent years because people found connections to cluster algebras and cluster categories. Yeah, let's see how this periodicity and glide symmetry works. So I've copied the Frieze again, and you see some region which I call a fundamental domain. It looks like a trapezium, and you can flip that over and then continue again. And with that, you can successively cover the whole Frieze. Let's do it blue. So that's called the fundamental domain. And the Frieze pattern is determined by any of those regions. But there are other ways to determine the pattern. Is you can find a path between the top and bottom row of ones. And once you have this path, like this one here, you get everything else using the diamond rule, because then you always find a new entry you can compute. And the third way to determine the pattern is just to look at 7 entries in the first interesting row. That's called Q, the credit sequence. And here I wanted to write the numbers. Let's just maybe do it that way. It's 3, 2, 2, 1, 4, 2, 1. Oops. I go back to the, okay, good. So because we have this symmetry, translation symmetry, we have m+3. If you find 7 entries here, it's going to determine all the rights, because you compute everything below using the diamond rule. Some first observations, you never find 1 next to 1 unless you're really in that row or in the last one. And in the yellow shaded fundamental domain, you should find exactly m occurrences of entry 1. So we had this 1, 2, 3, 4. Okay, I think that's all what we need here. And then one of the first questions that Coxeter asked and Conway and Coxeter then answered, how do these freezes arise? And the answer is that you can use a triangulation of a polygon. The size of the polygon depends exactly on m. It's m+3. So that brings us to the next page. Here I wrote the Q. This is this first non-trivial row. It's called a credit sequence. And credit means essence. Yeah, so what Conway and Coxeter show is that these Frieze patterns are in bijection with triangulations of convex polygons of the right size. And if you start, so here in my example, we had a 7, periodicity 7, because the rank was 4. So we should take a 7-gon, and I drew a triangulation of a 7-gon. And now if you look at this sequence, 3, 2, 2, 1, 4, 2, 1, well, you get it from counting the triangles that you see near a vertex. So at vertex 1, I see 3 triangles. At the vertex 2, I see 2. At vertex 3, I see 2. So we have 3, 2, 2. And then we have 1, and then we have 4, and 2, and 1. So that's how you get the bijection between the Frieze patterns and the triangulations. Yeah. So when you have that, well, it gives you a geometric combinatorial way to interpret the first non-trivial row of the Frieze pattern, but in fact, you can interpret any row of the Frieze pattern using the geometry or the triangulation. And that's what Broline, Crow, and Isaacs showed in '74. So if you have such a Frieze, then the entries in any row can be given by counting allocations of triangles. So here I was counting how many triangles I see. But if you go in row 2, you want to see how many triangles can I associate to 1 and 2, for example. So that was going to be this example. So in the second row, the entry 1, 4 would be, you look at between 1 and 4, we have vertices 2 and 3. How can we allocate triangles to this? Yeah, I'm going to make it bigger. I call that triangle 3, so you will have a 3 here and 4. So this is one way to attach a triangle to 2 and 1 to 3, or you can do 3 and 5, or you can do 4 and 5, and that's all. And then if you check later, this entry in the second row should be an entry equal to 3. So that's what Proline, Krauer, and Isaac showed, and in fact they also show it's symmetric. So if the entry in position 1, 4 is 3, then also the entry in position 4, 1. And that explains us the glide reflection we had before. Let's just make it short and write glide. Yeah. Okay, so these Frieze patterns, at some point they got forgotten because everything was explained about them, but then since the connection to cluster theory was discovered, the interest has been renewed. And because in cluster algebras or cluster categories you have mutation, or say exchanging of summands in a cluster tilting object, and that gives rise to the diamond rule. Now, these Friezes, which I've introduced now, these flat finite Friezes, they correspond to cluster algebras in type A. So here we have translations of polygons. But similarly, you can use other surfaces. I take a triangulation of a polygon like here with a puncture in the middle. And I can try to associate Friezes as well. So that's what you can do. You can associate Friezes to punctured polygons. They will correspond to cluster algebras in type D. So how does it work? Again, we have to count the number of triangles we see. So here we see 1, and then we have 2 at vertex 2. And then it's going to be too big, 3 at vertex 3 and 4 at vertex 4. And then I start putting, again, I drop the zeros. So there are zeros, ones, and then 1, 2, 3, 4. And then we continue with 1, 2, 3, 4, because now we only have 4 vertices and we go around. Then in the next row, we get 3, 1, 5, 1, 3. But then, because the underlying pattern should be corresponding to type D, so underlying here, we should see a quiver of type D 4. We have to split apart the entry, which in the flat picture you would have just had a 2. So using my previous example here, we would have a 2, he would have a 12, and here we would have an 8. But one can show that this gives us patterns where we really have, for each object in a cluster category of type T4, we have these numbers which sort of correspond to numbers of submodules. Yeah, when we found this, we played around with the patterns and we tried to multiply them together, these numbers. And we realized that the numbers just grow. They never get down to 0 again. So we get infinite Frieze patterns. Now again, they're flat, like in the beginning. And I've written it down here. So the 2, the 18, and the 8, which I indicated here. Yeah. And the numbers will grow forever. So what you can find here, there are a few things. First of all, it's not so clear how these numbers grow, but if I look at row 4 and row 2, I count from the first interesting row, I call this row 1. Then the row 4 minus the row 3, we have 13 minus 11 equals 2. And it's the same here, 7 minus 5 is 2. So this is constant. This difference is going to be constant. I don't know how I made this bigger. I hope I can go back again. Oh, good. But if I look in another row, like 3 and 1, here I have 4 difference, here I have difference 15. So that's really special. It only happens between row 4 and row 2. And then again, row 8 and row 6. And why is it 4? It's just a multiple of the period. We can explain that a bit better. So the infinite Friezes, I mean, we asked the question then, how can we get infinite Friezes? And the first source are these punctured disks, which come from the type D. So we assume we have a row of zeros, then a row of ones, and after that everything is positive integers, and we ask again for this diamond rule, which is, if you think of the module category, a small mesh or a mesh rule. Okay, so what my student Chabold showed is that triangulation of punctured disks always give infinite periodic freezes. But furthermore, you can show that in a diagonal, the entries grow linearly. So I'm just going to say it and not write it. And what does it mean to grow linearly? So she showed that we have arithmetic sequences in every diagonal. And I've highlighted 2 diagonals. So here, and you have to jump 4 steps or n steps, maybe I should. Plus n steps. I didn't really draw a new Frieze here. I just had to go down a bit further to illustrate the arithmetic growth or recurrence. So if I start with that row and plus 4, I get an entry 5, which coincidentally is plus 4. Then I go down another 4 steps and have again plus 4. But that depends on the diagonal. I took the yellow one. Here we have plus 6 and then plus 6. And you can check everything else. They are always going to be linearly growing when you go n steps down. So the tools to show this was to modify Broline, Crow, and Isaac's approach, and also some tools from Coxette and Conway, is when you look at the first row, if there's an entry 1, you can reduce the Frieze, so you can sort of kill that diagonal and the other diagonal, and you get a smaller period. In the process, this 4 will shrink a bit, become 3. The 2 will shrink again, become 1. And you continue until you only have 1 entry, which is just equal to 2. And that's a good exercise. Try to compute the Frieze with only 2s in that row. You'll find that it's just linearly growing and always plus 1 everywhere. But what you also observed is that not every infinite Frieze arises like that. So you can try out 2, 3. And the numbers are going to grow exponentially in some sense. I put the picture on the next page. Okay. So if I put 2 and 3, and 2 and 3, so it's just 2 periodic, compute the numbers, 2 periodic, you see that they grow much faster now. But we still have this nice pattern that when we go in row 2 and then subtract entry from row 0 above, that's constant. And because 2 was the periodicity. So again, and to make sense for that, I just extended the Frieze by a row of minus 1s. So here we add 2, then row 4, row 4 minus row, no, what was that? Sorry, that was the row 1. So row 2 minus row 1 is plus 4. And then row 4, so that's plus 14. So that's clearly not linear anymore. And so they grow faster, but we can still obtain them from some triangulated surface. If I look at this annulus, so I take a disk, cut out a little disk, and count the number of triangles on the outer boundary, they are 2 and 3. So what you can show is that every infinite Frieze can arise from a triangulation of an annulus. And the method is that you write down, the Frieze is given by this row, the quiddity sequence, A1, A2 up to AN. You write down A1, A2 up to AN in such a strip. And then you continue with A1 again to make it periodic. And you draw the numbers that you want. Like here it would be 3, 2, 4. And then you want to see triangles eventually. So you put little half edges for the diagonals, and then you connect everything. So that's sort of the main method. It also works if it's not periodic, but then you don't get a nice annulus. You just get a strip as a surface. Okay, so you can always do this. And we find that again, we have these constant differences. So row J times N, if we have N periodicity, minus entry 2 above is always constant. Call this as J. And in fact, these constant differences are Chebyshev polynomials in the first interesting coefficient. So here it would be in 4. Or we also wrote down a recursive formula, which might be easier to check. Yeah. And the important part is if this first interesting growth coefficient, because that's really depending on the quiddity sequence above, that's just always +2. If that's larger than 2, the entries grow asymptotically in that grow exponentially. And that's if and only if. So the linear growth is the boundary case, is when we have a +2. So you can go back and check the linear growth. There you should find that the first interesting coefficient is S1 equals 2. Yeah, okay. And that's a Chebyshev polynomial of the first kind. If you modify it slightly. Okay. But since we can use an annulus to get to an infinite Frieze, I didn't really say what happens on the other boundary. The annulus has 2 boundaries. So if we look at the inner boundary, we get another sequence when we count triangles. And here we have a 5, just 1 point. In fact, we get the quiddity sequence with only 1 entry. So this triangulated annulus always gives you 2 Friezes, and the question is, how are they connected? First of all, you can show that they have the same growth coefficients. So I should call that the growth coefficient. This first one. So that doesn't depend on which boundary you look at. Sorry, this is very awkward. I'm not gonna. So it's the same. S1 is the growth coefficient. And the question is, so in the finite case, Coxeter and Conway showed that the Friezes correspond to triangulations of disks, and we wanted to understand how infinite Friezes correspond to triangulations of annuli. So for every infinite Frieze, we find an annulus with a triangulation, and we get another Frieze for the other boundary. And what we can show is, if we have an infinite periodic Frieze with, say, quiddity sequence A1 up to AN, and if we assume that all these entries are at least 2, and not all equal to 2, that's this extra condition. I call that skeletal. When they're all equal to 2, they come from type D, and here I want to go to type A tilde. So I really don't want to have this nice 2 which came with the linear growth. But let's say we are in this situation, then there exists a unique triangulation of a corresponding annulus. with endpoints on the boundary outside, and you can determine how many points are inside, which gives you the frieze. And then there's also a unique counterpart, like the other frieze, which makes the pair for the annulus. So we have this skeletal triangulation. I should say what a skeletal triangulation is. All arcs are between the two boundaries. Let's say they are called bridging because they form a bridge. And I'm just going to go back to see the picture. So here, the arcs were all going between the two boundary components. If I had an arc on the boundary, that's called peripheral, and it doesn't really play a role. It makes an entry 1 in the quiddity sequence, but I can reduce. Oh. Can you hear me?
Yes, there was, for a few seconds there was some problem, but now I can hear you well. Yes.
But yeah, it's my internet is not stable. So, okay, so we have this skeletal triangulation. Again, all the arcs go between the two boundaries, and that's not a strong restriction because we can remove all the other arcs. They give us a pair of friezes, but they also give us a quiver on a cycle, which has an acyclic orientation. And we're going to see that on the next page. That's how we get to representation theory of A tilde. Yeah. And I wrote here up to cyclic permutation. I mean, the frieze is given by this quiddity sequence, but I could start at A1 up to AN or start at A2 up to AN, A1. So it doesn't really matter up to choosing the starting point of the cycle. And similarly, you can make the triangulation more curved by rotating the inner boundary, but that doesn't really change the properties of the triangulation. So to illustrate this correspondence between an acyclic orientation of a cycle or a frieze. So we start with the frieze, we draw the triangulation to it. This can always be done. And once we have a triangulation of a surface, we can associate a quiver to it. We look at any two arcs in the triangulation which are together in a triangle, and we draw an edge between them. So that's this blue picture. And the orientation I chose was clockwise. So in this little triangle, 5 is first, and clockwise we have 1. And that you can, so that explains the connection between acyclic orientations of the cycle, triangulation of the annulus, and the frieze patterns. And in fact, you can read off the quiver directly from the quiddity sequence. There is a method to do that, which I put here. You have to sort of walk along the quiver, and at every step, look how many arrows are going backwards. In some sense. But I want to talk about SLK friezes for a moment and then come back to this linear growth or exponential growth. So very similarly to the friezes we had before, you can look at frieze patterns where you look, instead of the diamond, you take a K by K matrix. So here, take some K by K matrix, and you ask that this has determinant 1. And you also want that bigger matrices have determinant 0. That's called a tame Frieze. Yeah, these have been introduced just after Coxeter introduced the normal Friezes. And one of the questions here is, how many Friezes do we have? Because before we had the correspondence with triangulations, and then we can count Friezes. And the other question is, how do they arise? So in general, when K is large, we have infinitely many such Friezes, and you cannot count. But in small cases, you can count, and actually we can use Grassmannian or Grassmannian cluster categories. Or if you prefer, coordinate rings of the Grassmannian variety to make Frieze patterns for SLK. I want to make this a little bit quick. So if you're familiar with the Grassmannian, so it's really an algebraic variety of k-dimensional subspaces of C to the n or R to the n. And in the coordinate ring, there are some nice elements which are called Blöcker coordinates, which you can think of coming from these wedge products in the exterior algebra. I'm just going to quickly explain how you get the Frieze and then continue. So these Blöcker coordinates Pi come from choosing k elements from 1 up to n. As I said, you can think of E1, wedge E3, wedge E4, for example. And we form a grid again, like in the Frieze pattern, taking these, say, 3 subsets here, which are almost consecutive. I have 1, 2, 3, and when I go one step up, I increase the last element. 1, 2, 4, 1, 2, 5, 1, 2, 6. So that's the +1 on the light blue arrow. Now when I go down in the grid, I increase all the other elements. So the 1, 2 become 2, 3. +1 on the k-1, which are neighbors. That's like just the setup of the lattice or the grid. And then we specialize the ones on the boundary, 1, 2, 3, 2, 3, 4, etc., to be equal to 1. And then we can show that this gives us an SLK Frieze pattern. So all the rest, as little k by k matrices, has determinant 1. And that just follows using the Blöcker relations in this coordinate ring. So now I was speaking about variables, but you can pick a nice subset of variables, which was like picking the triangulation. So you can pick a cluster, specialize that to 1, and that gives you a Frieze with integers to go away from the variables. Okay. And then we can start counting. So when k equals 2, we are back to the classical Frieze, Conway and Coxeter, and they correspond to triangulations. So they're counted by the Catalan numbers. And then there are 3 more cases where you can count. So 3, 6, 3, 7, and 3, 8. Now it's a little bit tricky. So the first number in each of these entries is coming from specializing a cluster to 1, like choosing a triangulation was. But then there are some Friezes where you don't specialize to 1. So there are special Friezes which are understood for 3, 6, and 3, 7, but not yet for 3, 8. Yeah. Here I drew these clusters, if you're familiar with that. So in 3, 8, we have one cluster which comes, or one Frieze which comes from specializing a cluster to 3, which is very exceptional. And that example is due to McMahon, or he found this. And I should also say this number of Friezes, they have really all been found in some simulation by Fontaine and Plamondon. It's just that we're not sure that they cover all existing freezes. So everyone believes this is the right number, but there could be more. Okay, but now I want to use just a little bit of time to talk about this growth again. Sorry, and I should not say linear, that is wrong. I should say with growth coefficients. The linear was really only when we talked about punctured polygons. So the infinite freezes come from triangulations of annuli. And we can use our results to show that they have a nice growth behavior. So they have these growth coefficients, and it doesn't matter which boundary component you look at. So both boundaries have the same growth. But you can also think, okay, I take some surface with arbitrary many boundary components, and that gives me more freezes. So I have one example here. We have a disk and two boundaries in the middle. We have three boundary components. That's also called a pair of pans. And I denoted the boundaries by delta 1, delta 2, delta 3. So if we count, and I drew a triangulation. We count at the outer boundary, we have 5. So that gives me a quiddity sequence of 5, and in fact gives me the growth coefficient immediately when we are in a one periodic freeze. And if I look at the other boundaries, so number 2 has 4 triangles and number 3 has 6. And obviously these 3 growth coefficients are different. So we don't have the uniform growth here, which we had in the annulus or in type A tilde. And since I said, well, the pair of freezes comes from a cycle with an unoriented cycle. I mean, like with an orientation which is not a full cycle. This has to do with representation theory of A tilde, and we can think of module categories with tubes, and we can look, sort of count submodules, like look at the mouth of a tube, and count the number of submodules for these objects, and that gives me a quiddity sequence. So this gives me all the time an infinite freeze. That's fine. But I should write here submodule count. But for example, I have looked at the Grassmannian cluster category where we have, again, tubes, and I took the numbers of the submodules at the mouth, and the growth coefficient was not uniform in general. So it is special for A tilde. In fact, we expect that tame module categories have the same behavior. Well, in some sense, in the tame module category, when you look at the tube of rank R, you know that everything up to level R-1 are rigid objects, and the growth coefficient really comes from that level where you stop having rigid objects. So what we found is when we go to the other tame types, D tilde, we also have uniform growth. So in D tilde, we have 3 tubes, 1 tube of size rank n-2, and 2 small tubes rank 2. And we computed their growth coefficients, and they're all the same. So that's very recent work. We have some examples in type E tilde where we computed, so especially in type E tilde, E6 tilde, where we computed the growth coefficients of the 3 tubes. So here again, we have 3 tubes, and we found that works. But the problem here is, So in type detailed, we can use the triangulation of a surface. So we can take a disk and have 2 punctures in the middle. And then we can start counting triangles to get to quality sequences. So that's in detail there. Say we need some points on the outer boundary. But for the E-types, E-tilde types, there is no surface model available. So we can start with some orientations and compute submodules, but it gets really hard. So we have to develop new methods. For example, if we know that from one orientation of E-tilde, we could go to another, and that the growth coefficient pattern stays nice on the mutation, then we could get everything. But that's work in progress. So, and I want to stop with this. Thank you very much.
So thank you, Karin, for your nice talk. Are there any questions, comments? So let me start. Karin, you say about the E-tilde. Do you have any Frieze pattern about type E also?
Type E, yes. I mean, sorry, I just have to stop.
Because as you know, there is some triangulation in type E, but in some sense, in some color triangulation, yeah.
Yes, we haven't looked at that. So you can consider in type E, you can just take the Ausländer-Reitenquever, and then you get Frieze patterns. And in fact, we looked at those because SL3 Friezes for 3.8, they correspond to the mesh Frieze on the Ausländer-Reitenquevers in type E, 8.
Yeah.
Or as I should say, in the cluster category of type E8. So that's true. There are colored, yeah, I should maybe compare that. Maybe one could use that even for E-tilde. There are
maybe there is some connection, there may be some connection between the color triangulation and this.
Yes.
That's right.
Yeah.
And the other question about the SLK Frieze. If we change the K and work on the division rings, you know what happened in general? Because in mathematical physics, there is some very nice space, and this space, in some sense, are equivalent to the Grassmannian, but Grassmannian not over the field. It's Grassmannian over the division rings.
Can you repeat? I didn't understand at the beginning, so now afterwards.
In SLK Frieze pattern, if you change the K and work with the division ring instead of the field.
What it does to the Frieze pattern, or?
I mean, the important part is the Grassmannian of the coordinating of the Grassmannian of this.
Yeah, but I mean the K. So it was like the size. So it is SLKN means K-dimensional subspaces of C to the N.
Yeah, but you work in a Grassmannian. You work or algebraic field.
Yes. Yeah.
But if you change the field.
Yeah,
and
and
we have and work with the division ring. In representation theory is similar to the works on a representation of a space.
Yeah, I don't really know what happened. I mean, well, here we use the algebraically closed field because we wanted to have some Crowe-Schmidt categories, but I guess for the Frieze patterns, that's not so important.
But in a space also we have a Crowe-Schmidt category. But for example, in thinking case, it's should be the quiver with the some weight.
Yeah. Like in B or C.
Yeah, B or C. Yeah, like
Yes. And there are freeze patterns for that as well. But I don't know whether the SLK freezes have been considered in that context.
Mhm.
Yeah.
But there is no SLK for this context. Only just SL2 for the. I mean, for example, for B or C.
Yeah, I think there's only the classical one at the moment.
Yeah, thank you. So are there any questions, comments? So if not the case, let's thank the Karin again. Thank you.
Thanks. I can stop that one. I don't know how you can stop the slides. So. Oh, that's, yeah. Okay. Yeah.
Thank you very much for the nice talk.
Yeah. Yeah, I didn't know that you cannot connect. Yeah, well, I think it worked now. I was going to write more, but it was okay. Yeah.
Okay, thank you very much. And to say bye, hope to see you in person. So bye.
Yeah, I hope so. Yeah, that would be nice. Okay, good. Bye.
Thank you.